At several points in this course, we have seen some of the ways in which symmetry can influence the outcomes of our calculations or of our evaluations of quantum systems. For example, we've seen that symmetry is really inherent in a lot of the selection rules that we find for spectroscopic transitions. So it's time for us to really take a deeper look at symmetry and try to quantify its effect and how it can be used to really understand something deeper about molecules. And I think the place to start is to first talk about what is symmetry. How would we characterize that? I realize that this is one of those things that you know it when you see it, but how would you actually explain it to someone who, for example, maybe couldn't see it? Well, here's a possible definition that one could use. If I wanted to say, what is symmetry? It's basically when we have recurring patterns in an object. And I'm going to make up some terms that probably you won't find in books, but I'm going to say that these recurring patterns identify something that I'll call equivalent microenvironments or microfeatures. And we'll say that these pertain to a physical object, of a physical object. Now, what do I mean by this equivalent microfeatures? Well, I think it's easy to say, for example, if I have a rectangle, that in some sense I can divide this rectangle in half, and I have one half over here that is equivalent to this half over here. So there is some sort of symmetry relationship between the two halves of that rectangle. So that's maybe an overly simplistic picture of this, but it gives us an idea that what we're looking for is a piece of an object that repeats itself several times within that object. But moreover, there's another important aspect to this. It can be transformed into those repeats in some sort of operational way. For example, in this case, I could simply reflect these two halves across this center line of this rectangle, and I would get the same rectangle back. So the whole idea is that we want to identify these equivalent microfeatures and be able to transform them into a new location or exchange them with one another, but not change the overall object. So I've used a lot of words to describe this. I think really the easiest way to see this in action is to begin to look at what this means or what this implies. Now, in doing this for molecules, one of the first things I need to state up front is that we're not going to treat molecules as they really are. We're in fact going to treat molecules as though they are fixed objects. That is to say, they are not vibrating, they are not rotating. Well, I guess they could rotate, but they're not changing their overall shape. They're fixed objects, and they're going to be frozen at their equilibrium geometry. So even though other geometries may be very important in understanding the behavior of molecules, in the case of symmetry, we're really just going to care about what they look like at their equilibrium, and we're going to treat them as though they're like little statues frozen in that particular geometry. Now, I'm going to define two different things that help us understand something about the symmetry of a molecule, or of any object for that matter. And these two things are symmetry elements and symmetry operations. Now, it's useful for you to know how these are distinguished from one another. A symmetry element is simply a geometric feature. And this geometric feature could be a point or a line or a plane, something like that, that is embedded in the molecule and provides a connection between what I've called equivalent microfeatures. All right, so in case of this rectangle, it was this plane here would be the symmetry element. All right, and that is the thing that relates the left side to the right side. All right, what about a symmetry operation? Well, a symmetry operation is the transformation of these equivalent microfeatures into each other. So in the case of our rectangle again, the plane that divides the rectangle in half is the symmetry element. The act of reflecting one side to the other side is the symmetry operation. Right? It may seem like it's silly to to define these as different, but we'll see that in fact the symmetry element is going to be different in the sense that it is a geometric feature. In this case, it's a plane. A symmetry operation is actually something that moves the atoms, even if hypothetically, to a new location in the molecule. All right, let's look at an example, and it's one that we have seen, for example, when looking at some of the molecular orbitals. So I want to consider a pi star orbital. Okay, and remember the pi star orbital, we have two nuclei, and they have lobes like this. Now, in the case of the pi star orbital, the lobes, say here and here, have a positive sign, and then the lobes on the opposite corners have a negative sign. All right, so in this case, there's no way I can just rotate simply, for example, about this axis or about this axis, and reproduce this wave function. Okay, it does not have a rotation axis in that sense. But what it does have is a center of inversion. So for example, we had noted that the pi star orbitals we would denote as pi sub g. G being Garada, meaning we can have inversion between two things that are on opposite sides of this inversion center that's in the middle here. So in this case, our symmetry element is this point. And the symmetry operation would be the act of taking this lobe and moving it over here, and this lobe and moving it back over here. All right, so the element is the point, and the operation is actually the exchange of these of the lobes of this orbital. All right. Now, obviously, this is just one of many possible elements. I want to give you an idea of what some of the elements are that we're going to be talking about, and how and the ways that we refer to them symbolically, so that we can all be speaking the same language and writing the same thing. Okay, there are several different elements that we will be caring about. One is the simplest and is also perhaps the most trivial, is the identity element, which we give the symbol E. All right, it results in effect in no change to the positions of the atoms. That is to say, it's just like multiplying by 1. But it turns out, in order to have the properties of a group, and that's what we're going to care about, we need to have this element present. All right, a second one, and this is the one we saw in the rectangle, is the reflection operation. This element we give the symbol sigma. Okay, and so that represents the plane, and the operation would be reflection through a plane. Okay, so maybe I should put a heading over here that the operation it corresponds to. And these are the elements. All right, next we would have inversion. We've looked at that. Okay, the symbol that we give an inversion center is little I. Okay, don't be confused with the complex number square root of -1. This little I is simply the inversion center, so it's inversion. The operation would be inversion through the center. I should note that this, when a molecule has this particular symmetry element, that element is always located right in the middle of the molecule. That is, the geometric or geographical center of the molecule is where that would be located. All right, the next one would be a proper rotation. And that proper rotation might be given the symbol C sub n. Okay, and this represents rotation about this axis. This is an axis in the molecule by a quantity that represents 360 degrees divided by n, or 2 pi over n. All right, finally we have something called an improper rotation, and that's given the symbol S with the subscript n, and that's basically a rotation like Cn, so rotation by 2 pi over n, then a reflection through a plane perpendicular to this axis. And we'll see what that looks like in another video. Now, each of these, as I've written them, these are the symbols that we use to denote these particular symmetry elements, but I want to distinguish them from the operations. There are going to be times when I want to specify this as an operation, and when I do that, I'm going to do it in the same way we do it with quantum mechanics. I'm going to put a little hat over it so that you'll know that we're talking about an operation. All right, so in each case, this is what these things would look like, with a little hat over them to indicate these elements. Now there's one other thing that I'd like to point out, and that this improper rotation, imagine that we had an improper rotation with n equal to 1. Okay, so let's say n equals 1, so I have the improper rotation 1. Well, what would that be? Well, I'm rotating by 360 degrees, so it's a rotation by 2 pi, which just takes you back to where you started, and then reflection. So if the rotation hasn't changed the molecule at all, then this just becomes a reflection. So S1 is equivalent to a reflection. Well, what about n equals 2? Well, S2 would now be a rotation by 180 degrees, or by pi, and then reflection. And it turns out that this is exactly the same as an inversion. So S2 is equal to I. All right, so if I can express these in terms of S, it means that really, if I wanted to, I could do all of my operations expressed as either a proper rotation or an improper rotation. And we aren't going to play much with that, but I thought it was very interesting for you to grasp that this improper rotation actually is a more general sort of symmetry operation and symmetry element than may appear on the surface. Anyway, we're going to dig deeper into these in the course of this lesson, and so I hope by the end of this lesson you'll be very familiar with all of these.